piecewise functions and continuity. This is going to give us an opportunity to look at proving things, something you'll do far more in university calculus. So let's graph f of x equals negative x if x is less than 0, x squared between 0 and 1 if x is bigger than 1. This is what I'm asking for. We have three different graphs we're looking at. The function negative x. This is positive x, so negative x looks like that. The function x squared, it's that one. And the function 1 is this one. What we're going to do is just take the part of this graph where x is less than 0. So this section right here. So we're going to take that and put it on our graph. Then we're going to go between 0 and 1 on this one. So between 0 and 1, it would look like that. And then from 1 on, we take that graph. So it's known as a piecewise function. You've taken pieces of different graphs and put them on one. And that's a much nicer version of the graph. All right, what are we going to do with this? We're going to look at whether the function is continuous. And there's a very technical definition of continuity. Three things must be true for a function to be continuous at a point. First of all, the function must exist. So let's look at a graph where this is not true. Imagine you had this, a hole in the graph, and then the rest of the graph. The function does not exist there, and that is why we'd say that one is not continuous. In order to be continuous, this point must exist. The limit must exist. Here's a graph where that is not true. What if we had a graph that did this, and then went from there to someone else? You can see that that graph is not continuous either. And that limit, we're not approaching one single value. So that's why it's important for the limit to exist. Otherwise, it absolutely cannot be continuous. Now, what if these two are true? The limit exists and the function exists. They actually have to be equal to each other. So here's a situation where they're not. This graph has a hole in it, and the point is up here. So the function value exists. The limit exists, but they're not the same. That creates a hole, which makes it not continuous. So in order to be continuous, the function value must exist, so we can't have holes. The limit must exist, we can't have breaks. The function value and the limit must be in the same place, so we don't have this situation. The points we need to check, anywhere we jumped from one graph to another. So 0 and 1 are the potential places for breaks in this graph. Let's talk about how we check. We said there were three things that had to be true. The function had to exist, the limit had to exist, and the limit and the function had to be the same thing. So which one of these three has x actually equal to 0? I would say right here. So we're checking the function x squared when x is 0. Put in 0, and you get an answer of 0. So the function value exists and is 0. What about the limit? We're going to check from both sides. X smaller than 0, that would be this one. So we're checking this one first. The function value, we're plugging it into negative x, and we get 0. Then we'll check from the right, bigger than 0, that's our x squared again. Plug in 0, and you get 0. If the two limits are the same, if we're approaching the same thing on both sides, then the limit exists. Does the function value equal the limit? The answer is yes, therefore it's continuous. And let's double check that. That is what we expected. We expected at 0 that the function would be continuous. Okay, let's try and do the same thing at 1. At 1, does the function value exist? When we're equal to 1, we're talking about this function. So plug in 1, you get an answer of 1. Does the limit exist? We're going to check from the left and the right. Smaller or equal to 1. That's still x squared. The answer is still 1. Bigger than 1. The function is the function 1, which means always equal to 1. So that answer is 1. As you approach from left and right, do the limits equal the same thing? Yes. Therefore, the limit exists. And then, does the function value equal the limit? They both equal 1, so they equal each other. Conclusion, the function is continuous at 1. Let's double check that and see if that's what we expected. And the answer is yes. If you're having trouble at all saying, ooh, I really don't know where you're pulling these functions from, let's see if we can take a look at it from the graph. Let me get a highlighter out and show you what I'm doing. The function value at 1. I'm looking for x equals 1. And that is the function x squared. So this function is the one where it had an equal sign on 1. That's where we're plugging it in then. Approaching 1 from the left-hand side, as you're coming from the left, can you see that the function you're on is the function x squared? As you approach from the right-hand side, that's this function. Right-hand side of 1 is the function 1. That's why we're plugging that in. Let's try another one. First, we need to graph it. We've got 3 functions. We have the function x squared, x cubed, and 2x. Okay, so x squared we know is a parabola. X cubed, that's a cubic function. 2x minus 1 is a straight line, slightly steeper, and then drop down 1. If we put the pieces together, what do we end up with? We want the x squared graph from -1 to the left. So that would be at 1 and it would go up. We want the x cubed graph from -1 to 1. So that would be from here to here. And then we want the 2x minus 1 graph when we're bigger than 1. I wonder what value that would be. If we put 1 in there, we'd be at 1, wouldn't we? Okay, so that's at 1. So it looks like it might do something like that. So we think this is what our graph is going to look like. So we're expecting it not to be continuous here, but we believe it'll be continuous there. Let's see if we can prove that. So the 2 points we need to check, anywhere we jumped from one graph to another, we must verify that it's continuous. Why don't we have to check the other ones? All these polynomials, x squared is continuous, x cubed is continuous, 2x minus 1 is continuous. So the only possible places this could not be continuous, as long as we're looking at polynomials, is where you jump from one to the other. So let's check at 1 first. Equal to 1, that's right here. So we're looking at x cubed when we're equal to 1. Plug in 1 and we get a value of 1. Let's check from the left. Smaller than 1, that's the same graph, smaller than or equal to 1, so that's still 1. Bigger than 1, that's this one. Our function for that is 2x minus 1. Plugging in 1, we get 1. Are the limits the same from left and right? Yes, so the limit exists. And does the function value equal the limit value? Looks like it, doesn't it? They both equal 1, they're equal to each other, so we are continuous at 1. Is that what we expected? Yeah, good work, guys. Okay, let's check at -1. Equal to -1, that's right here. So the function we're checking is x cubed. Plug in -1 and we get -1 for the value. Approach from the left-hand side. Smaller than -1 is this one. So smaller than -1, we're checking x squared. When we square -1, we get 1. Bigger than -1, that's this graph, that's x cubed. We're at -1. Do the two limits equal each other? They don't, do they? So therefore, the limit as you approach -1 of this function does not exist. Why is that? A limit is a unique value. We cannot have two different values, so the limit does not exist. Is there any point in continuing? You have to prove all three to be true to be continuous. The minute something does not work, you can simply answer, it is not continuous, and you do not need to do any other work. So we're not continuous at -1. Is that what we expected? Yes, it is. So your job today, exercises 1 to 5. Fabulous opportunity to practice your graphing, put pieces together, and then try something that you're likely to see at university. How good are you at reading these graphs and understanding when you have to check for the actual function value? You're looking for equal signs. How do you calculate limits going from left and right? And can you check that the two are equal to each other? This is going to be a terrific exercise for you. Have fun.